Chapter 2 is the logic of compound statements. Section 1 is the logical form and logical equivalence. All right. So, let's see, an argument it's a sequence of statements. And the purpose is to demonstrate the truth of an assertion. Demonstrate truth. Okay. The final assertion is the conclusion. And all the previous assertions are the premises. In logic, the form is distinguished from its content. So we use variables to isolate the content and work with the variables in various ways to demonstrate truth or untruth of an assertion. You dropped a. So analysis will not help you determine the intrinsic merit of an argument's content. It will help you analyze the form to determine whether the truth of a conclusion follows necessarily from the truth of the premises. Logic is the, how's it worded here? This science of necessary inference. Of or the science of reasoning. And you let variables represent components of an argument. For example, let's give a quick example. If the bell rings or the flag drops, then the race is over. So you'll let P equal the bell rings. Q equal the flag drops. And R equal the race is over. So You can manipulate those variables in logical statements and arguments without having to be bogged down by what the variables actually mean. Symbolically, you go through the argument, and at the end you conclude with these three little dots, and that is equal to therefore. So if the let's use if the bell rings and the flag drops, the race is over. So getting a little ahead of things, but this could be rewritten as being P or Q, then R. If P or Q, then R. This V here is the symbol. V looking symbol is the symbol for or. How many have taken digital logic already? Oh, only a few of you. Okay. We'll get into the ors and ands and nots later. So we'll table this again. But another way to state this is, if the race is not over, then the bell hasn't rung and the flag hasn't dropped. And you could also have this, or you could also have the same variables but different content. So say x equals 2, x equals minus 2, and x squared equals 4. If p equals x2, q equals x equals minus 2, and r is equal to x squared equals 4, this same statement can be used. So you isolate the content of the variables from the actual argument and the statement. And we'll get into how to manipulate this later on. But either way, it's if P or Q, then R. Therefore, if not R, then not P and not Q, which is the equivalent statement. So if not R, if x squared is not equal to 4, then P is not equal to 2, and x is not equal to minus 2. So it can go either way. Another example. If Jane is a math major, or Jane is a computer science major, then Jane will take Math 150. Jane is a computer science major, therefore Jane will take Math 150. So P Jane is math major. Q equals Jane is comp sci major. R, Jane will take math 150. Okay. So if P or Q, then R, and if that's true, and Q is true, therefore R. So it is the same form as the following example. If logic is easy, or I study hard, then I will get an A in the course. I will study hard, therefore I'll get an A in the course. It's just a matter of different statements for the P, Q, and R. But the form, the logical form, is the same. Now, a statement or a proposition is a sentence. Let's see here. A proposition is a statement that is either true or false. It can't be both. Compound statements use symbols to represent, and I showed it to you a couple of boards ago. Compound statements use operators compound statements use these operators to link and manipulate the different variables of the compound statement. This symbol, which is the upper left-hand corner of your keyboard typically, is the not symbol. The up angle is the and the down angle is the or. Easy way to remember the difference is and is like a large A without the crossbar, and or is the other one. So, like I said before, P or Q is true, or the equivalent was not P and not Q. These two are not actually equivalent, but in the example, these were both used. So the order of operations goes from is similar to math. Regular math classes, you do parentheses first. So if you do like this and R, you evaluate what's inside the parentheses first, and then you do the operations outside the parentheses. The next order of operation is the not. So not P is evaluated before the and in this situation. And the not Q is evaluated before the and. And or are co-equal in their order of operations, but that they are the last. Let's see here. I'm sorry? The equivalent, and an or. They're done at the same time. But you use parentheses to indicate, like in this situation, the or goes first and then the and goes second. Whereas if you were to have the parentheses here, the and would go first and then the or. It just depends on the parentheses arrangement. Let's see here. Let's say, everybody got this? Yeah. Let's say H is it is hot. S is it is sunny. Now, if it's on a cloudy Mississippi summer day, it would be hot and not sunny. Oops. On a clear, this is, it is hot, but not sunny. Or on a clear winter day, you could say it is not hot and it is sunny. So, let's see here. A little bit of terminology. The and is called a conjunction. In this case of not H and S. If you were to say it is neither hot or sunny, it is neither hot nor sunny. Well, actually, I have the it is not hot or sunny. Let's see here. That is a disjunction. Of H and S. Or is a disjunction, and is a conjunction. Now the truth tables, here's a definition from the slides. A statement form or propositional form is an expression made up of statement variables and logical connectives, and or not, that becomes a statement when actual statements are substituted for the component statement variables. The truth table for a given statement form displays the truth table, the truth values that correspond to all possible combinations of truth values for its component statement variables. So, the truth tables. Let's go ahead and put those up on the board.
Okay, so or is the disjunction?
Yes. Yes, or is the disjunction, and is the conjunction. So you have not, which is A is either true or false, and the not A is false, true. That's the truth table. If A is true, not A is false. If A is false, not A is true. Like I said, this is just kind of, mathematically formalizing common sense. If something is not true, then it's false. If it's not false, it's true. So, and that's the A, B, A, and B. True, 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 false, false, true, false, false, true, false, false, false. In order for A and B to be true, both A and B must be true. Then A and B evaluates to be true. Otherwise, A and B evaluates to false. A or B With A or B, if either A or B is true, then A or B evaluates to true. If both A and B are false, A or B evaluates to false. Like I said, it's pretty much common sense. You know, if one or the other is true, then the whole statement is true. But you can use these three operators to create any kind of logical statement in different forms. So, let's see here. Let's look at a statement, an expression, and evaluate the truth table for the expression. Okay. Everybody got this yet, or still working on it? Still working on the truth table? I'll give you a minute or two. But the idea is you have your inputs, all possible combinations of the inputs, and the results for each combination. So if you have two statements, you're going to have four possible combinations. The number of combinations, incidentally, is number equals 2 to n to the n, where n is the number of inputs or statement variables. So if you have three statement variables to construct a truth table, you would need 8 lines. 2 to the third is 8, so you would need 8 combinations of A, B, and C, for example. 4 would be 16, 2 to the fourth. Anything beyond 4 variables is kind of cumbersome because it gets kind of large, as the truth table does. So the idea is to reduce your count in such a way that you don't lose any information, but you can do it more easily with fewer than 16 or fewer combinations. All right. All right. So let's see here. P or Q. P or Q. And not P and. Oops. And Q. So we have 2 variables. You're going to have 4 combinations of true and false. we'll do P, Q over here. True, 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 false, false, true, false, false. And then you break it down into its different components to construct the truth table for this expression. Let's take the first element, P or Q. So P or Q. And from the previous screen, the result of P or Q is true if either one is true. So true, 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 false. And then you look at this other one over here, P and Q. And from the previous screen, you get true, true, false. False, false, and false. Then you take the negation of that. Did I type this in right? Yeah, I guess I did. And then you take the negation of that. Oh yeah, okay. Not P and Q. Just invert all these. So false or true becomes false. False becomes true. 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 Then the final expression, and here, and these two together. Don't have room to write it, the whole expression. So P, first one, true, false, with the and is false. True and true is true. True and true is true. False and true is false. So that is the resulting truth table for the expression. Anybody have any idea what that expression is called? What that function is? Somebody from digital logic recognize that truth table? P and Q evaluating to these? That's the exclusive OR. The result is false if the two inputs are the same, and true if they're different. Exclusively or, not and. So that's a function that's used commonly in digital logic. Okay. Let's see here. Let's see here. Definition here. Two statement forms are called logically equivalent. if and only if, how does the slides, if they have identical truth values for each possible substitution of statements for their statement variables. If and only if they have identical truth tables. Truth table results. The logical equivalence of statements of forms P and Q is denoted by writing P triple equals Q. Two statements are called logically equivalent if and only if they have logically equivalent forms with identical component statement variables. When identical component statement variables are used to replace identical component statements. So you can test the equivalence of two statements by comparing the truth tables of the two statements and seeing if all the entries are the same for each of the matching input values. So let's see here. De Morgan's law. The negation of an AND statement is logically equivalent to the OR statement in which each component is negated. And the negation of an OR statement is logically equivalent to the AND statement in which each component is negated. So what that means is A and B the negation of an AND statement, so negation of A and B is logically equivalent to not A or not B. And the equivalent for the OR statement, A or B negated, is logically equivalent to not A and not B. I will leave that as an exercise for you to demonstrate the equality using truth tables. Do a truth table for each of these, and you can see that you'll see that this and this are the same, and this and this, the truth tables are the same. So, but that's yeah, Morgan's laws. Got a little example for you. Let's see here. X is is greater than -1, but less than or equal to 4. So -1 x 4 less than x is less than or equal to 4. Okay, so let's make P equal to X is greater than -1, and Q equal to X is less than or equal to 4. You see where I got that? I broke this up into two component variables, component statements. X is greater than -1, and Q is X is less than or equal to 4. So I just took those out like that. Okay. Now the negation of that, of this would be X is less than or equal to 1 or greater than 4, right? Yeah, that's simple algebra inequalities. So the initial the initial negation would be not P and Q. If X is not greater than -1 and less than or equal to 4, right? So the negation is equivalent to not P or not Q by De Morgan's law up here, the first one. So the result is not P, which is X is less than or equal to -1, or X is greater than 4. We got the not P and the not Q. And then you or them together. Okay? Now you have special circumstances. I'm sorry? Special circumstances. A tautology, there's a word for you. Tautology is a statement that is always true. And then you have a contradiction. Is a statement that is always false. These are abbreviated with a small t and a small c. An example of a contradiction or a tautology. P or not P. One of them is always going to be true, so the or statement will always be true. So that is, what is that called? That is, the negation law. All right. Let's see here. Let's see. A contradiction. Always a contradiction would be P and false. That is a contradiction. Both input variables must be equal to true in order for an AND statement to be true. Therefore, if one is always false, then the result of the AND statement is false as well. It is a contradiction. It is going to be always false. That can be also expressed as P and C equals C, and that is called the, what is that called? Oh yeah, okay, it's over here. That's it. Or you can also put it P more close to what the book says. Is P and not P. That is a contradiction. That is always going to be false, because if P is true, then not P is false, and therefore the AND is false. If P is false, not P is true, but that means one is false, and the AND statement evaluates to false all the time. That's a variation of the negation law. There are 11 laws on logical equivalence. Kind of cumbersome to put them up in the up on the board all at one time, but the section 2.1 slides has that list of logical equivalences: the commutative law, associative law, distributive law, identity laws, negation laws, double negative law, idempotent law, universal bound law, De Morgan's law, absorption laws, and negations of tautologies and contradictions. basically, the important ones that you need to remember are the distributive law, where P and R or Q is equivalent to P and R. Let's see if I'm remembering this right here. Yeah. Or P and Q. In this regard, you can think of this as being similar to the distributive law in algebra, where this is the multiplication and this is addition. P times R or Q, R plus Q is equal to P times R plus P times Q. Right? Isn't that the way the distributive property works in algebra? Pretty much. That's an important one to remember. Double negative law, an inverse of an inverse is the same as the original. Something anded with itself it remains itself. Something ored with itself, it remains itself. Yeah. But yeah, like I said, the slides on Canvas in the files section for chapter 2, section 1. I believe it's the last slide of the section, contains all of the laws. Leave it to you to go through and make note of all of those. I think we have time to cover conditional statements, or at least part of it. Conditional statements if P then Q. If P and Q are conditional statements, the conditional of P by Q is if P then Q, or P implies Q, and that is denoted. I showed this earlier, but more formally, it's the arrow, the right pointing arrow. It is false when P is true and Q is false, otherwise it is true. We call P the hypothesis or antecedent. Or antecedent. And Q is the conclusion or consequence. The consequent. Now, here's the thing. If a conditional statement has a false hypothesis, the overall statement is true by default. It is called being vacuously true. So, if 0 equals 1, then 1 equals 2. That statement is true. This is one of those things that's kind of hard to wrap the head around. But this statement is true. Because this is false, it doesn't matter if this is false. It doesn't matter what this is. The overall statement is true. Because the hypothesis is false. The conditional is true. So the overall statement is true. This is not saying that the second statement is true. It's just saying that the conditional is true. The truth table for the conditional operation. P, Q, P implies Q. If P then Q is, if they're both true, then the conditional is true. If the hypothesis is true, but the conclusion is false, then the conditional is false. And if the hypothesis is false, it's automatically going to be true. Vacuously true. True by default. In the order of operations, the conditional is performed last. So, let's go ahead and do a quick example. P or not Q implies not P. So, we'll do P, what was that? P or not Q, not Q implies not P. Okay, so got P, Q, and true, 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 false, false, true, false, false. Okay, so we perform first the negations. So let's negate Q and P. Not P and not Q. So that'd be, not P would be false, false, true, true. Not Q would be false, true, false, true. Okay? Now we'll do the OR because that's the next in order of operations. So P or not Q. P or not Q. P is true, Q, not Q is false. That would be true. P is true, Q is true, and or not Q is true. That's true. P is false, not Q is false, so that would be false. And then false and true would be true. Now for the final, P or not Q implies not P. So not P, true and true is let's see here. Okay, true and false. True implies false. That's false. True implies false. That's also false. False implies true. That's true. And true implies true. That's true. You see how I got those? You just step it through the order of operations, adding a column for each step along the way. Last column on the right is the resulting, the truth values for the entire statement. And to get to get a little bit of ahead of the game, you can see that this would be the equivalent. This is logically equivalent to this because the columns match row for row. So you could replace this entire conditional with not P and eliminate the Q altogether. Does that make sense? Yeah. We'll get into the reduction of expressions a little bit later on in the semester. But I think we'll call it a day here. Next time we'll do logical equivalences involving conditionals. But we just started with that just now, but we'll go in more in detail on Thursday.
Yeah, we said we can get this, let's say logically equivalent, we can get rid of the
Q altogether, because this here is equivalent to not P alone. So you could just eliminate the Q altogether. So there you go. Okay. We'll get into, like I said, logical equivalences involving conditionals on Thursday. In the meantime, have a wonderful weekend, or have a wonderful week. Too early for the weekend yet. But see you Thursday.